What up, everybody? Welcome to the IAG Thursday Thing. This thing that we do every Thursday, where we get together. We try to hang out, have a good time. Hopefully, we don't get too much reverberation through the other person's mic here. I'm yelling at you, sir. Um, but we've been pretty good and staying on schedule this week. Again, warranty is adulting. Sounds like producer Jordan is getting a little healthier, but isn't quite there yet. And we definitely want to thank Randy for making the thumbnail, even though he was very grumpy about it this time. Uh, this week, this is something I've been wanting to do for a while, and I'm happy we managed to find some time to do it. And it works out really well. But I keep getting a ton of questions when I'm talking to people about. I'm having a conversation with them about basic tuning concepts and terms that you can tell are no longer common knowledge. So, what I figured we'd do today is I'd bring on Graham from Boosted Performance Tuning. What up, Graham? How you doing?
What's up, dude?
All right, and then I'm going to just throw a shitload of basic tuning terms, words, things that are used that maybe you don't, maybe you understand, maybe you don't. I might even learn something here, who knows. We're going to try to answer a bunch of these, and maybe this becomes a source for people in the future to use or hand to somebody who maybe doesn't quite get a lot of these terms. So all right. So, we're just gonna start off from the top. One, Graham, thanks for being on. Who are you? Where are you from?
Graham from Boosted Performance. I think people know me probably in here.
Yeah, you would hope, but maybe this is our first time listening to this. So,
yep, been doing the tuning thing for a while now. I think it's been about 12 years. So,
yep, you've been at it for a minute. Graham Sue tunes boogie, and a pretty large majority of at least my customers, and he's been around the block. So him and Kim have been at it for many moons. So you're the perfect person to have on for this. We're gonna keep it real simple though. First thing I want to start with, okay, and we're just gonna start this real quick because a lot of people are probably gonna be listening to this are gonna be very new. Okay. When do you need a tune? I have a simple answer to this, but I'm interested to hear yours.
Okay. All right. When do you need a tune? Well, that's a good question.
Going back one. You're a tuner. What is a tuner?
Do you want me to answer that
I want you to answer that first. Answer that first. You are a tuner. Okay. What is a tuner?
What is a tuner? Okay, so tuning, the term tuning, a fancier way to say it is doing calibration. Mm-hmm. You're doing engine control unit ECU calibration. And what that means is you're changing the way the programming in the computer works to change performance or change drivability or fuel economy or account for different modifications someone's done.
Oh, perfect.
So,
all right. When do you
what a tuner is.
When do you need a tune then?
Well, you need a tune if you want to change parts on the car for the purpose of gaining performance. In a lot of cases, you need the tuning to be to adjust for that. Let's take a turbo car, for example. You want to put a aftermarket downpipe on it, more free-flowing exhaust. A lot of times that's going to affect the way the boost pressure works. And so you're going to, at the very minimum, need some tuning to take care of that. And a lot of times you're also going to want to raise the boost pressure, get more performance. So you could say that you need a tune if you're going to modify the car, but you could also say you need a tune if you want more performance out of your car. You don't really need it, but you want it.
Okay. So how I've explained this to most people, customers who are calling for parts and stuff, anytime you change air going into the engine or exhaust going out or changing fueling in some way, so you're adding more fueling as in larger injectors or something like that, or the type of fuel, you need a tune. So air going in would account for intakes, turbochargers, inlets, intercoolers, exhaust going out, headers, downpipe, catback. And some of these you can fall within margin, but for the most part, these are the basic rules, okay? So there's a very good chance if you change anything, any one of those, you should probably at least have your tune looked at. Is that fair?
Yep,
Fair assessment?
that's very fair. Yep, absolutely. Yeah, and more so on Subarus than other cars if we want to get into that.
Yeah.
Yeah. A little side note is the more intelligent and better programmed the ECM to begin with, the more modifications it can take without tuning. Subarus are on the other end of the spectrum where we're going to get into mass airflow. They're mass airflow based. So that means intakes can change the way the fueling is calculated or the airflow is calculated. They can be really sensitive on the boost control side of things because they have kind of clunky OEM boost control systems. As a comparison, a lot of German cars, you can change the intake, the exhaust, the intercooler. You can do all kinds of things on some of these German cars, and the ECU will account for it very easily and run perfect.
Yep.
Subarus are not necessarily that way. So it kind of depends on the platform as to how needed tuning is.
The vast majority of people listening to this is a very Subaru-oriented podcast. If you change something going in or you change something going out, it's probably going to need a tune.
That's typically how we explain it, with some exceptions that we can definitely cover.
Or like a catback or whatever. But
yep.
For the most part, if you're doing any one of those, it would behoove you to at least ask. Okay. The main device that the tune alters things is normally the O2 sensor. Okay? What is an O2 sensor? Usually, where is it located and what is it doing?
Sure. Okay. So the O2 sensor or oxygen sensor, its purpose is to figure out what the air fuel ratio is. Make sure I'm trying to explain this accurately, but also not
get too far.
Not in too much detail, but basically it's monitoring the exhaust so it can determine how well it calculated the airflow and how well it mixed the fuel in to achieve a given air fuel ratio target. And for idle and for cruising, somebody super smart worked this out to where approximately 14.7 parts of air to fuel works out to be a perfect burn, if you will. And that achieves the best fuel economy, typically with some exception, and also achieves the least amount of emissions. So an oxygen sensor is there to make sure that the fuel and the air are being mixed at the desired ratios for those purposes.
Okay, but that doesn't mean you want your car running at 14.7 parts to 1 part fuel. 14.7 to 1 their fuel ratios all the time.
Correct.
So typically
that's the best ratio for a complete burn, but that is not the best ratio for the best torque, nor is it the best ratio to avoid detonation on high compression or turbocharged vehicles. So what you're alluding to is correct. That air fuel ratio needs to change in the rich direction given those conditions.
Depending on what's going on. So, what is lambda?
So lambda is a universal way, regardless of the type of fuel, to express the mixture that achieves that perfect burn. So lambda is a scale that starts with basically one lambda being the perfect burn. And then depending on the type of fuel that you're using, for example, pure gasoline with no ethanol in it is that 14.7 to 1 on its gasoline scale. Pure 100% ethanol, for example, is 9.0 to 1. And ethanol blends in between are somewhere between 9.0 and 14.7. So 50% blend would be halfway between those two numbers. I don't know off the top of my head, but
Yeah.
you get the point.
Yep.
Propane has its own, methanol has its own. Every possible combustible fuel has its own ratio that achieves that complete burn and is one lambda no matter what you're looking at. So lambda is basically a lot of ECUs. In fact, I don't know if I want to say a lot, but as far as I know, all OEM ECUs under the covers care about lambda. Now, if they have flex fuel logic built in, they'll have some Stoich ratios and different things like that. Different ECMs do it different ways, but they'll equate gasoline ratios and ethanol ratios and things like that. But when the ECM is looking at the O2 sensor, it's looking at it in terms of lambda because that's a simpler way to do it, is my understanding.
Well, I mean, if you think about it, it's like just from a numbers standpoint, an ECU trying to figure it out, it's either going to be, 1 point and some stuff or point something and some stuff, So it's instead of it trying to like calculate a ratio, it's just doing a number. So
yeah, it's probably just because it's a more data accurate way of doing it.
Sure,
is probably what you'd boil it down to.
Yep. All right. So again, a lot of these are going to be super basic, but we're going over them. What is lean?
So lean is a relative term, and so is rich. So all that means is that what's ending up coming out the tailpipe through the O2 sensor has been mixed with less fuel than you intended. So, but for example, let's say you're trying to idle the car at 1 lambda or 14.7 AFR, and you're looking at it and it's 16.0 AFR. That's lean. That's leaner than you want to be because you want to be 14.7. Alternatively, let's say you look at your AFR and it's 12.0. That would be rich. That's richer than you're intending. But let's pretend that you're going full throttle and your target is 11.0. If you're ending up at 10.0, that's rich. If you're ending up at 12.0, that's lean. It just means that you're mixing less fuel than your intended target, and the O2 sensor is showing you that.
There you go. All right, next one. Another fairly basic one, but it really matters. What is timing?
Timing. Okay, so, well, it depends. Are we talking about ignition timing, fuel injection timing, or cam timing, Dewey? Because it matters.
Nope, this is great. And this is the conversation we're going to have. Now, most of the time when people start talking about timing, when the term is thrown around, the majority of the time, they're talking about ignition timing. But you're right. All of these things matter. So,
yep, there's a lot of different timings in modern engines. But
so
yeah, let's focus on ignition timing.
And then let's glaze on the other ones, but let's just touch them real quick.
Sure. Okay. So ignition timing. So as soon as engines got past the point of having distributors and they started having digital ignition, the computer is basically controlling when the spark plug gets energized. And that matters because you need to ignite the fuel mixture well before the piston reaches the top, generally speaking, especially at lighter loads. But as you have a higher load, as you have, let's say, more boost pressure in a turbocharged engine, you don't want to light the spark too early. You want to light it closer to when the piston's coming up and getting ready to, reach the top dead center. So, so when you talk about timing, a lot of people, if you're like, oh, how much timing are you running? Generally, what they're asking is, how much ignition timing are you using at full throttle, at your full load? So let's say you're running 30 PSI of boost pressure and someone says, well, how much timing did you put in it or did you run? You might say, oh, well, and this is a pet peeve of mine. And this exists so much for some reason in the domestic world is, I'm running 20 degrees. And I'm like 20 degrees, like everywhere, like at 4,000 RPM and 8,000 RPM. Like you can't say I'm running 20 degrees of timing.
Yeah.
That doesn't make any sense. Now you could say, and a lot of times what they mean is they're like, I'm running 20 degrees, meaning the highest amount they're reaching anywhere at any RPM at peak RPM is 20.
Maximum amount of
The maximum amount is, but that matters. But at the same time, on a manual transmission car where you're sweeping through some different RPM ranges, it matters what the timing curve is, because you're going to have more ignition timing at higher RPMs because the engine is spinning faster, for one, so you got to start the spark sooner, and for two, you tend to have higher exhaust back pressure, less efficiency, so you need to start the spark sooner for those reasons anyway, to make the best amount of torque you can. Whereas at low RPMs, things are more efficient. You don't start the spark as early. So, if you say, how much ignition timing am I running at 30 PSI? You might say, well, this turbo is making 30 PSI by, let's say, 4,000 RPM, and I'm running 10 degrees of timing there. And then I'm kind of tapering it up slowly to 6,000. And then after 6,000, I'm ramping it up to 22 degrees. You would describe your timing curve. If you want to describe it accurately, you describe it in a manner like that. It's going to have typically a curve to it that's going to represent the efficiency of your setup. Does that make sense?
Yes. So let's say we're at a given RPM, and let's say we're talking 20 degrees of timing. So the concept here would be the spark plug would be energized 20 degrees before top dead center. Okay, meaning the piston, well, I'll just explain what top dead center is. The piston is at the top of its stroke. Okay, it's all the way at the top. So that is 20 degrees before it reaches the top. So we're about to go into detonation and knock, and some of this will come into play, but I want to make sure we understand when we say timing, when you're talking about timing or you hear somebody spitting timing out, more than likely what they're talking about is ignition timing, and that is the spark plug is going off a given amount of degrees before the piston reaches top dead center.
Yep. Okay. And do you want me to touch on fuel timing and cam timing real quick?
Yes.
Okay. So cam timing, that's definitely a more common thing. A lot of, almost all modern engines have variable valve timing, or AVCS, as Subaru calls it. And that's basically, that's phasing the camshafts in relation to top dead center as well. So if you say that my VVT is at 0, generally the 0 position is the center line of the cam in relation to top dead center. And if you say, if you're talking about intake cams, they move in an advanced direction, which means they're basically opening earlier. So if you say I'm running 30 degrees of AVCS advance, that means you've used the solenoids and the fact that the cams can move when the solenoid gives them oil pressure, and you're moving the cam in the advanced direction 30 degrees for the purpose of creating some overlap, scavenging effect, generally spooling the turbo quicker potentially, or having more mid-range torque by taking advantage of scavenging, and then you move the cam back. So if someone talks about cam timing, they're talking about how they're advancing their intake cam for the purpose of making the best torque. And if you talk about the exhaust cam, generally exhaust cams move in the retard direction. You're basically delaying when they open, again, for the purposes of extra scavenging by being able to phase 2 camshafts, or sometimes they move it in the other direction to hold the charge in a little bit. That can be beneficial too. So that's cam timing. And then injection timing is something that we didn't really talk about much in the past with port injection, because it's not super important. There's kind of a broad window of port injection timings that work. And to be honest, to some degree, you can almost just, outside of maybe idle and light loads, you can pretty much spray a port injector almost any time you please, and the fuel will get in when the valve opens.
It'll figure it out.
It'll figure it out. There's some menial gains by playing with it at full loads. It's something I experimented with in the past, and I was like, yeah, there's really not much difference here. But when we start talking about modern vehicles like the FA engines with direct injection, the timing of the injection becomes critical, because now these are like diesel engines where we're spraying the fuel in the cylinder, and when we start spraying and when we stop spraying is super critical. There's only certain windows of time. So when people talk about injection timing on direct injection, that's a very critical component that also gets measured in relation to top dead center. So if you say, I started the injection at 360 degrees, that's 360 degrees before top dead center. And then if you say, I ended the injection at 80 degrees, you ended it at 80 degrees before top dead center. So that was your window of injection. So those things all play into this as well, especially in relation to spark, because you got to make sure you don't keep spraying your fuel when you're trying to light your spark. So it all kind of goes together. But that's going to get real high level if I keep going on that.
Yeah,
but that's
don't go too deep
injection
into
timing.
that. Now, what I would like to talk about real quick is port injection versus DI, or direct injection. DI gets thrown around a lot, and a lot of people don't understand the difference and why it's the positives and negatives of both. I'm not telling you to go deep down here, but if you could quickly explain port injection versus direct injection.
Yep. So port injection, that's traditional, like most folks are used to on an EJ engine, where you're using low pressure, and I'm saying low pressure relative to high pressure direct injection. You're using low pressure fuel injectors before the intake valves, spraying the fuel into the air. The valve opens, it goes in the cylinder that way. Yep. Direct injection, the injector tips are pointed directly inside the combustion chamber, and they're spraying the fuel at very high pressure, like 2,000 to 4,000 psi, directly into the cylinder.
And they are
that's
literally
the difference. And then you've got some engines that have both.
Yes. So, like, an example of all three here is the EJ engine. So any STI we got here in the States, WRXs before 2014 and earlier, yada yada yada. Anything with an EJ, port injection. Okay. And then you have 15 to current WRXs with FA20s and FA24s. Those are direct injection only. Okay. They don't have port injection from the factory. They're direct injection only. And then you have the BRZ, FRS, GR86. These are kind of the oddballs, and they have direct injection and port injection. So they have both. So within our Subaru sphere, we actually have all three types, which is kind of odd, but it's the truth. What I will say real quick, just from an aftermarket standpoint, not to drive the tuner up the wall, is it is super easy to upgrade injectors comparatively in a port injection car versus a direct injection car. So if you want to add significantly more fueling, it's way easier in a port injection car, but direct injection actually has a lot of positives. And he could go into tuning and all of this, but there are a lot of positives with being able to run higher compression, doing some tricks to keep knockdown. We're going to go into knock here in a second. A lot of cool stuff you can do with direct injection, but they have their positives and negatives, and it's something you need to take into account. It is significantly more expensive to upgrade direct injection versus port injection. Okay, here we go. We took care of top dead center. What is boost?
Boost. Oh man, that's our favorite term around here.
That is the word of the day.
So boost, yeah. So boost, what you're doing there is you are grabbing the air around you. The turbocharger's grabbing the air around it and compressing it so it can get more of it into the cylinder.
Yes.
So you're basically it's an atmospheric multiplier is one way to look at it.
As a tuner, when you are measuring boost, what are you measuring?
So we are measuring the relative amount of pressure above and beyond atmospheric pressure. And you'd be surprised how many people don't realize that when you're sitting there in a room anywhere, there's the air around you is actually pressurized. We're sitting here. I'm sitting here in about 14.3 psi of air pressure around me as I talk to you, and so are you. If somebody is sitting in Denver, they're at approximately 13.3, and if someone's really high up on a mountain, maybe they're at 11.1 psi of pressure. But there's already pressure in the air around us. Otherwise, we wouldn't be able to breathe, and engines wouldn't run because you wouldn't be able to combust that's getting a little bit far down the rabbit hole. But anyway,
Yes.
a turbocharger, what it does is it takes that and it compresses the existing air more so that it can fit more of it into the cylinder. So when you say boost, you've got to look at what your relative pressure is and then how much you're going above that. So that's where we get into the conversation of what is manifold pressure versus boost pressure.
We're getting there.
And we're getting there. So if you look at a naturally aspirated car and you look at the manifold pressure sensor gauge, when the engine's not running, it's going to be sitting there at 0 because it's going to be showing you relative essentially to the engine not running.
Yeah, basically air pressure, like normal
then when
ambient
you start it, you're going to create vacuum. And by the time you go full throttle, you're going to be back to 0 essentially. So boost pressure starts from when you start making positive pressure above that. So your manifold pressure, let's see, hang on. I'm explaining that poorly. So manifold pressure would be in a naturally aspirated car sitting at around, let's say, sea level, which is, let's say, around 14.4 psi of, not directly sea level, which is about 14.5 or whatever, but it would be sitting there. The manifold pressure sensor would be reading 14.5 absolute pressure. As it goes into engine vacuum, you would see 8 to 9. As you go full throttle, you'd go back towards 14.5.
Mm-hmm.
On a turbocharged car, you'd see the same thing, except that when the engine starts to create enough exhaust to spool up the turbo and create positive pressure, your manifold pressure would start going above 14.4. So let's say it goes up to 30. Then you would say, you would do the math and you would subtract 14.4 from 30 and come up with approximately 15 psi of boost. The boost is the pressure being created above and beyond your atmospheric pressure.
Yes. Now, there's a difference between boost and volume. Okay, so boost is a measurement, no matter which way we look at this, is a measurement of resistance. Okay, so it's measuring pressure depending on where your boost gauge is. It's measuring the air pressure at that point. Okay, so but air pressure and boost doesn't necessarily mean you're going to be making significantly more power. Okay, so let's say we have a VF30 or a VF39 off of an 04 STI. Okay, and that at 20 psi is not going to make anywhere near the same amount of power as a Garrett G35 1050 at 20 psi. The volume's different.
That's correct. This is actually a pretty fascinating thing that we can kind of touch on a little bit. Again, it gets to be a pretty deep conversation, and this is something that kind of, if you will, can sort of keep me up at night a little bit.
Yeah.
And I've had this conversation with other really high level tuners, and we've all kind of racked our brains on this. And if anybody in the comments knows more than I do about this and wants to chime in, certainly can. But the conversation of what exactly are the elements that cause a bigger turbo at exactly the same boost pressure to make more horsepower than a smaller turbo at exactly the same boost pressure? What exactly are the elements? Because if you look at, we're going to talk about speed density.
Yes.
If you look at the speed density calculations, it doesn't take into account turbocharger efficiency. It's just manifold pressure. The pressure is the pressure.
Yep.
And at certain RPMs and at certain efficiencies, sometimes 20 psi on a VF and 20 psi on a G35 1050 could make closer to the same horsepower. Now, as you start to spin that out, if you were to try to force a VF turbo to make that higher boost at the same RPM that 35 can, which isn't even possible, first of all, really what's happening here is it boils down to what the term I like to use called pumping losses. How hard is the engine having to push to make that 20 psi? And if you where high level ECUs and account for this is when you add a exhaust pressure sensor and you start to tweak your calculations for that. Essentially, the bigger turbocharger at the same boost pressure is a lot easier for the engine to push and to pump, and you're not losing as much power through that effort. Does that make sense?
Yes. So
that's kind of what it boils down to.
No matter which way you look at it, an engine's an air pump.
That's correct. But what I've come to learn is more of it has to do with the exhaust and the exhaust pressure side than on the actual intake side. The compressor side of a turbocharger will definitely control, how much boost pressure it can make and how it can make that boost pressure within limits of turbo shaft speed, and also like things like transient response and at what RPMs it will come alive and so on and so forth. But a lot of the power potential comes down to the compressor side and how efficiently it's set up. And it's all back and forth, give and take to pair the right compressor with the right turbine, and size it to the engine and the use and the RPMs. It's there's a lot that goes into it.
There's a lot. This is so I'm without going too deep down the rabbit hole. There's a reason that these giant turbocharger companies exist, and they hire like NASA people to design these things. The math that goes into it is an absolute mind screw, and honestly, I would love to have some engineers from Garrett on here to blow our minds. They have a much better explanation of that than we do.
An interesting test we did was when we tested the Gen 2 G35 against your Gen 1.
Yep.
And we found that at the same boost pressures, it made exactly the same horsepower.
Yes.
Even though there were some people that were pretty convinced it was going to make more power at the same boost, it didn't. What it did do was it did make the same power with way less shaft speed.
Yes.
So we were able to increase your shaft speed, increase your boost pressure without breaking the turbo in half, and make more power. The power came from the extra boost. The ability to add extra boost came from more efficient turbine wheel or whatever else in there to allow us to make boost with less shaft speed. So that's a component too.
It absolutely is. And there's again, we're talking math that's really hard to, I'd love to have a Garrett engineer on here. That's way, way down the rabbit hole for us today though. So we're going to continue on. All right.
Yes, let's move on.
Yes. What is detonation? And or the term pre-detonation, which gets tossed around, please go into that too, even though like we're going to piss Dom at, get a Dom tune off.
Yeah, there's a lot of different ways to describe this and explain this. And, I'm just going off of kind of like how my brain likes to think about it. So sure. I may not say it exactly correctly. I don't
think anybody is going to. It's just, how Dom gets when you say pre-detonation. He like
but so I'll try not to speak too technical so no one calls me out on it. But basically what it boils down to is that the fuel, and I gotta make sure because Tim's in here, and if I say the explosion happens when if I call combustion explosion, Tim gets really upset, so we can't do that. So what essentially happens is your combustion. We can all agree that the term is combustion.
Yes.
Your combustion is happening before you want it to. Okay, and so that begs the question: well, when do you want it to happen?
So real quick, I'm going to just answer this term. Combustion is basically your fuel igniting due to your spark plug. Okay.
Yes. You're burning the fuel. You're igniting the fuel. However
yes.
I like to say you're exploding it because it sounds awesome. It sounds like you're having a nice explosion in there to get some more, whatever.
If you say explosion around Tim, he wants to throw wrenches at you.
He gets upset. I think to me, it's all the same.
I think it's the same.
You are igniting the air fuel mixture.
We're blowing shit up.
And when do you want to do it? Well, you want to start the combustion process at a point where it releases its maximum energy at a point in which the piston has already reached top dead center and is starting to move back down. And if the focus of the energy happens way after top dead center, when the piston, let's say, is halfway down the bore, that's going to work, but it's not going to make as much torque because the energy of the combustion event is not pushing on the piston at a time in which it can transfer as much energy into the rod, into the crankshaft, and so forth. So the perfect point is you kick off the combustion event a bit before top dead center, and as it's releasing its maximum amount of energy, the piston has reached the top and is heading down, and you get the maximum torque at that point. So that is controlled combustion. That is what you want. Detonation is when the energy gets released before the pistons come to the top. So essentially that's what you're dealing with there. As far as why does that happen, it can be a lot of things. If you're using way too much ignition timing, if you're straight up lighting the combustion off well before top dead center on a particular load charge that doesn't need that needs to be lit quite a bit closer to top dead center. So let's just, in terms of ignition timing, let's say that, again, let's just take some random engine and let's say 4,000 RPM, 30 PSI, and someone is putting 20 degrees of ignition timing into the tune. That's probably on almost any engine going to be releasing its energy well before the piston reaches the top. Let's say that, the ideal timing, the perfect amount of timing that makes the most torque, where 1 degree less makes less and 1 degree more doesn't make a difference. Let's say it's 10 degrees for this magical engine, okay?
Sure.
If you're running 20 degrees when 10 degrees is what's ideal, it's going to explode the fuel before it reaches the top. And that's going to create a nasty noise that's known as knock and picked up by the knock sensor.
You're doing a
because
great job.
The explosion is basically hammering itself into the piston that's trying to come up and then rather than go down. Does that make sense?
Yes. So basically, the ignition, the combustion is happening before it reaches top dead center, and it's trying to smash the piston basically in the wrong direction. And it makes a sound that we refer to as knock. What is a knock sensor then? And what are knock counts as you see them on an access port or something like that? Like, there are two different types of knock that an access port shows, but can you explain those real quick just so somebody's listening, they understand what knock is?
So the knock sensor, I don't know, I can't remember the term off the top of my head for them. It's a type of sensor, but it bolts to the engine block, and it's listening
You just
within
said
certain
from there. It's essentially a microphone. The easiest way to explain this to somebody who's new is a knock sensor is essentially a microphone.
Yeah, there's a more advanced term for it. It's I can't remember what the heck it is, but it is, yes, essentially a microphone bolted to the block that listens within a certain frequency range that is based on bore diameter and some different harmonics. Basically, your bore stroke ratio goes into the calculation, some other stuff, but it listens within a certain frequency for a given engine, and it's looking for it's measuring in voltage, and it's basically the ECU is looking to see within a normal range. There's always going to be some noise on the knock sensor just hearing the engine, but when the voltage spikes above the expectation, that's considered to be a knock event. It doesn't always necessarily mean it is. It could be hearing a rattly clutch or something else or whatnot, but generally it's going to have to assume it's knock, especially if it continues to see that signal and across multiple cylinders and for longer periods of time. It's going to start to react to it and assume that it's detonation.
So if your ECU's microphone, aka the knock sensor, starts seeing frequency ranges that are falling within the spectrum of what it may perceive as knock, and there's lots of different things that can cause this, including knock.
But no, it's listening within a certain frequency range, and what it's looking for is
outside of
basically it's looking for the noise within there to spike up.
Okay.
It's listening for the sound that detonation makes, which
Yes.
sounds a little bit like shaking rocks in a can,
Yes. So it's
in
listening
my
for
opinion.
it's listening for said term, knock.
Yep.
Your ECU then can make changes as needed. It doesn't necessarily mean your engine has exploded. It means that your ECU sees something that it feels it needs to make a change for, or at least monitor.
Yeah, and basically it's adjusting your ignition timing generally, and in some cases on some other ECUs, it might actually start adjusting your boost pressure, even your fuel curves, in those cases.
All right. One thing I want to throw out here too is since we're talking about detonation, knock, and I want to go over dam real quick. What is dam?
Damn. Okay, so that is
This is
a
another
lot of these.
this is
What's that?
another very Subaru centric term as far as I know, and this is going to
Yeah, it
apply
is.
more to access port people.
It is. So I'm gonna explain what this concept is that exists in pretty much any production ECU,
Sure.
OEM ECU,
And
and then
then
I'll explain it in how Subaru has implemented it. So
perfect.
in pretty much any road going OEM ECU in modern times, they have to be able to account for different octanes essentially. So even if it's a performance vehicle, we know that in some places like Alaska, you can only get 90 octane. In a lot of places you get 93, in some places you get 91. So they can't give out, when you buy your Subaru, you don't say, "Hey, I run 93. Could you hook me up with the 93 car in the lot?" It doesn't work like that. The ECU has to be able to account for these different octanes, and to some degree, even account for people who might ignore the premium sticker and put 87 in their Subaru that's turbocharged. So all vehicles have this concept of a kind of what I call an octane learning. The whole purpose of this is to try to determine the quality of fuel that someone's running and dynamically, this is where the dynamic advancement part comes in, dynamically adjust the settings, how the engine's running to account for it, primarily by reducing ignition advance. And again, also to some degree by possibly reducing boost pressure and using richer fuel targets, like we talked about earlier.
Yep.
Subaru does this with a number called the dynamic advance multiplier. On the early Bug Eyes drive-by cable cars, this was a number that moved between 0 and 16, where 16 was maximum and 0 was minimum. On all the all the drive-by wire cars, it's on a scale of 0 to 1, where 1 is maximum and 0 is minimum. And the way it works is if you look at the tune, there's a base ignition table that has your timing advance in it, and then there's an additive table, the knock advance table, that has some other portion of timing in it. Typically more heavily weighted in the high load areas. So in the low load areas where there's not typically knock, the advanced table might not have any of the timing. It might just be 0. But let's say in the high load areas at full throttle, there could be anywhere between 4 to 12 degrees of ignition timing in the advanced table. And the advanced table gets multiplied by the advanced multiplier before it gets added to the base table. So let's just say at a given spot in the advanced table, it's 5 degrees. If your dam is 1 times 5 is 5, that carries over. Let's say your dam drops to 0.5. It would take 0.5 times 5, and you'd only get 2.5 degrees of that timing. And the dam is applied all the time. So it's a way to basically create a global reduction in your ignition advance in order to try to avoid detonation from lower quality fuel.
Real quick, I want to touch on octane and quality fuel, and I can take this one real fast. Octane is highly misunderstood. I'm sure you're going to hear some old timers say, well, once a month I throw premium in to clean her out. That really makes zero sense. Okay. What octane is, if anybody was wondering, when you're looking at an octane rating, the higher the number is, the more resistant the fuel is from going off at the wrong time. So the higher the octane, the more resistant it is from detonating and or, combusting at the wrong time. Okay. It's more resistant fuel is the easiest way to look at it. This is why you cannot put lower than recommended octane specs into your engine and expect it to work correctly, and or not damage it, because if it's too low of an octane, that fuel will detonate or combust, at the wrong time, and it will cause boatloads of knock. And when your engine is knocking, this is when you do massive damage to your engine, flat siding bearings, blowing, ring lands out, all of that noise. Okay. So the octane has a lot to do. Now, going back to this, we did skip something real quick. The access port shows two different ways of looking at knock. You have knock and then find knock learn. Can you explain what find knock learn is so people aren't freaking out if they get a little bit of find knock learn?
Yeah. So
Or see
yes,
knock
the
count
dynamic
here every
advanced
once in a while.
multiplier is kind of the global term,
Yep.
is the global thing. And then there's two other things. One of them is the feedback not correction, and the other one is fine learning not correction. So these are pretty simple to understand once I explain them. Feedback not correction is instantaneous. It's as simple as the engine heard a certain amount of noise from the knock sensor, it determined to be knock, and it does immediate corrective action of reducing ignition timing in that moment, which is shown as the feedback knock. So a small noise, but higher than the threshold, might result in a -1 in feedback knock, and that means that 1 degree of timing is being reduced. So if that spot in the tune as it's going calls for 11 degrees, and you see a -1 feedback, it's going to change from 11 to 10. It's going to wait a little bit longer to light the combustion charge to hopefully stop it from being lit too soon and detonating, if that is indeed what's happening. If that number starts to go down to -2, -3, -4, then it's getting more aggressive with reducing the timing advance, again, with the hopes of fending off the detonation that it believes is happening. So it does that on an immediate basis. If it stops hearing the noise that it believes to be knock, it will start to take that away and go back towards a feedback knock reading of 0, which means no intervention's happening. And that's basically feedback knock. It tends to lean on that when it believes that it's just kind of some light knock that it can handle. It will lean on the advanced multiplier when it's hearing very heavy amounts of knock and it believes that octane is low. It will lean on that. Fine learning knock is the third thing, and essentially what that is, as the name implies, it learns to reduce timing in a certain area. And the way this works is, if it, through some logic in the ECU, if it continues to hear knock in a certain spot, which is generally kind of a matrix of load versus RPM, it will start to build up some fine learning knock in that area. So maybe -1, -2. So if you sweep through the RPMs and it's hearing a lot of knock, it might start reducing that fine learning knock, let's say to -2 in a given spot. Then when you go back through that same area again, that -2 will be applied immediately, and then additional feedback knock might come in from there. Conversely, as you continue to go through that area, if the ECM is not hearing anything it believes to be knock, it will slowly take that -2 and work it back towards 0, essentially. So that's basically, feedback is immediate. Fine learn is remembered correction in a given load and RPM area. And your advanced multiplier is basically your effective octane handling system, if that makes sense.
Yep. All right. We got to go over onto the intake side of this thing now. Okay. What is a mass airflow sensor, or a MAF? When somebody's talking about a MAF, what are they talking about?
Sure. So obviously, like the probably one of the single most important things that an ECU is doing is determining exactly how much molecules of air, or grams, or however you want to measure it, is going into the engine at a given time. So it's basically, an ECU is an airflow calculator, a really fancy one. And there's a lot of different ways to figure out how much air is going into the engine. And one of the simplest and most straightforward is actually a mass airflow sensor. What a mass airflow sensor is a little device that protrudes into the airstream, typically on the intake side of a turbocharger, if it's a turbocharged engine. And what it's doing is there's a wire that's a very tiny little wire that gets heated. And as air passes over the wire, it cools it down. And the sensor measures how much it's being cooled down, translates that to a voltage, and that voltage maps to an amount of airflow. You wouldn't think that a little hot wire sitting in an airstream could really be that accurate at measuring airflow, but it can. So that's what a mass airflow sensor is doing. Telling the ECU how much air is coming past it.
Yep.
Plain and simple.
So if somebody were to go, you've heard the terms MAF housing or big MAF.
Yep.
Essentially what they're talking about is sticking the mass airflow sensor in a larger housing. But when you do that, you then have to recalculate what that mass airflow reading is.
Yep. So this is a good one. Let's talk about exactly why that is.
Yep.
So when Subaru is doing the OEM calibration, they're sticking a Denso MAF sensor into their airbox, and that airbox, at the end of the airbox has a round section that is the MAF housing. It is a given diameter, approximately 67 or 68 millimeters in diameter. The mass airflow sensor goes into it directly into the middle, and then they do their measurements, and they map the voltage from the sensor to an amount of airflow in grams per second. If you make the MAF housing diameter larger, what happens is you are slowing down the airflow, so it's not moving past the sensor as quickly, and so it's not cooling the wire as quickly, and it's sending off a lower voltage. But in reality, you have the same amount of airflow going past it, so you have to recalibrate the scaling to account for that. And it's to kind of get a starting point. If you put a 75 millimeter housing on, you can do some math where you essentially square 75 and square 68 and divide it, and that kind of gives you a starting point by how much to scale up the math. And then you use data logging, you use the O2 sensor readings and the fuel corrections to fine tune from there. The benefit and the reason of going to a larger intake isn't always necessarily to get more air in the engine, but it's because mass airflow sensors have a voltage range. And if you put a larger turbocharger on there and start sucking more air through a stock intake, you might reach a point where you reach the voltage limit of the sensor and therefore can't raise your boost pressure, can't make more power. So putting a bigger MAF on there basically causes it to bring the entire voltage range down and allows you to continue to read the higher amounts of air going in the engine without maxing out the MAF sensor reading.
Well, you nailed that.
That's mass airflow. Yeah,
that's mass airflow.
It works great. So, the other thing to mention too is that the mass airflow sensor also contains another sensor, which is the temperature sensor for a Subaru. So it also tells the ECU the temperature of the air heading into the turbocharger.
So this is something that I don't think people deal with much at all anymore, but was a massive problem when we first started messing around with larger turbo kits and things like that on Subarus. What is a blow-through MAF? And essentially, if somebody is referring to a blow-through mass airflow, what are we talking about here?
So on a stock Subaru and on most vehicles that I'm aware of that run mass airflow sensors, they're going to be on. If there's a turbocharger involved, the mass airflow sensor will be in front of the turbo. So basically, that's considered draw-through, meaning that the turbocharger, as it's pulling in its air, is drawing the air through the MAF housing past the MAF sensor. If you switch it to a blow-through, what you've done is you've taken that MAF sensor and you've placed it after the turbocharger before the throttle body. So now you're measuring the air at that point. Now, that said, it's if you put it in the same size housing and you move it, it's going to be reading similar. The benefit might be that you might have less turbulent air. So back before speed density, when people were putting bigger turbochargers on these cars and doing rotated, what ends up happening is because it's a straighter shot into the turbocharger, you put the MAF sensor on there and try to read the air coming into the turbocharger, you start to get you start to get I just said it, my brain lost it. Turbulence. You get more turbulence as the turbine wheel is spinning up and slowing down that can screw with the MAF reading because the air starts moving essentially not just in one nice direction, but it might reverberate back in another direction, back out essentially and throw the readings off, and the car doesn't want to run as smoothly and as well at light loads. So blow through MAF became a solution to that by moving the MAF sensor over close to the throttle body after the intercooler, after everything else. It's typically just seeing the air move in a consistent direction into the throttle body, which improves the airflow reading, which improves the way the car runs at light loads. So that's why blow through MAF became popular. The other benefit too is then you are taking your temperature sensor rather than measuring the temperature of the air coming in the engine. You start to measure the temperature of the air going into the turbo. You measure it going into the engine. So you can use the temperature sensor rather than just, as an idea of how hot the air is in the engine bay or outside, but you actually know how hot it is going into the engine. So you can change your compensations to be more aggressive if you've got high charge temps. So there's a benefit there. So that's kind of where blow through MAF came in.
So, we need to explain MAP. Okay, MAP sensors, because then we're going to go into speed density. So, what is a MAP sensor?
MAP sensor is the manifold absolute pressure sensor. So pretty much any modern engine has at least one, if not multiple, pressure sensors, typically just one manifold pressure sensor. That is measuring the amount of pressure that exists inside the intake manifold. So specifically after the throttle body, but before the intake valves. Knowing the pressure of the air inside the intake manifold is pretty much critical to calculations on any modern ECU. So even a naturally aspirated BRZ has a manifold pressure sensor, even though it also has a MAP sensor. It still has a MAP sensor. Turbocharged vehicles always have MAP sensors because they have to know the pressure to essentially control it and limit it if it's running too high, things like that. So MAP sensors there to tell the engine the amount of pressure in the intake manifold.
All right. So one of the downsides with blow through MAFs, as we had to deal with back in the day, there's a few downsides. One of the big ones is turbochargers tend to, there's always going to be a little bit of oil, thrown. And when you get oil on a mass airflow sensor, or anything on a mass airflow sensor, this is why you keep them clean. Because it's just a hot wire, if there's something on there, it's not going to read correctly. So if they get crowded up, they get oil, all sorts of stuff, it'll start affecting the reading. Well, blow through MAFs have a serious issue with being in the path of a turbocharger. They're probably going to get some oil residue on them more quickly than you would usually prefer. And it would throw the readings off quite a bit. So, there's other advantages to that too, but I'm glazing over this. But one of the big things, and when it happened, it was huge, is us being able to finally switch Subarus over to speed density. Now, this really didn't start. This wasn't a thing outside of standalone engine management. This was always been a thing in like Hondas and stuff like that. But for Subarus in general, we didn't really start getting to play around with this till like 06, 07, something like that is when they, like, the access port finally made it something fairly easy to start messing with.
I think your timeline's a little early. I don't really remember it coming around until closer to like when I had my 2011. I feel like speed density was
it was definitely earlier than that, because I know at
no
least we were
way.
doing speed density. We were doing speed density tunes with Carberry's ROM way back in the day.
Yeah. Yeah, because right, that was kind of a unique situation, but like a
That's
US like an '05 STI, like when do you think we could do '05 STI on speed density?
hmm.
I don't feel like that was until closer to 2011
Oh, I bet
because I
you.
remember
Man, it had to have been like at least 08
I don't know, man.
with the
Maybe
GR.
somebody in the comments knows.
I would like to know
I
that. That's a good question for anybody in the chat or listening to this or
when
somebody.
did
If you
Cobb
want to
speed
leave a
yeah,
comment,
specifically
leave a
when did
comment.
Cobb speed density come out? I
Yes,
don't think I think it was closer to 2010 to 2012.
it's okay. Probably right. Maybe I'm wrong. Either way, we didn't get speed density forever. And I remember when it finally happened, it was like, oh my God, the world is so much simpler now. Okay. Explain speed density and what changes. And we're talking about Subaru specifically. What is speed density?
Okay. So well, look, somebody like 20. Oh, Marshall. Oh, wait, hang on. Somebody dug it up and someone said 2010. That sounds about right. Anyway, speed density. Okay, so speed density is a completely different way of calculating the air going in the engine. It's significantly more complex, but it gets around some of the limitations of a mass airflow sensor. It arguably isn't necessarily always as accurate, especially if we start talking about part throttle, but it's beneficial again to avoid MAF related limitations. Let's just kind of say that. But essentially what it's doing is it's using the ideal gas law and it's taking in the variables manifold absolute pressure, like we talked about. So the pressure of the air in the intake manifold. It's also considering the temperature of that air. The temperature suddenly becomes important in the calculation. The ideal gas law is factored in. The size, the displacement size of the cylinder. So how much volume there is to fill in. And then the element that gets tuned is the volumetric efficiency of the cylinder at a given manifold pressure and a given RPM, typically. Again, if we're just making it really basic.
Yes.
When we start talking about, using Mtron speed density model can take in other variables and can, like the exhaust map sensor and things like that and supplement and calculate and give us more accurate. But let's just talk about in the context of Cobb. Okay, Cobb added speed density to the factory ECU that doesn't have it at all, and did so by writing their own custom code, and they implemented speed density in the simple manner that I'm describing, where they use the ideal gas law. You tell it the displacement size. So if you have a 2.5, you put in 2.5. If you swap a 2 liter in, you say 2.0 and 2.35 and so on. So you specify the displacement. And then primarily you have a table that's your volumetric efficiency table that's based on manifold pressure and RPM. At your idle areas, your efficiency is really low because the engine you can't get as much air into the cylinders at lower RPMs. And then at a point where you are into your boost pressure and you're at your most efficient point of your setup, your VE number will be the highest. As your exhaust pressure comes up, again, we were talking Cobb here, you can't measure it.
Yep.
So as you go into higher boost pressures and you start getting less efficient, your VE comes down. And as you spin the engine out to higher RPMs where it's less efficient, your VE also comes down. So now, rather than just having a simple 2D table to map a MAF voltage from a mass airflow sensor to an amount of air, you're having to tune in this 3D table to get the fueling to be correct by calculating the airflow correctly. So from a tuner's perspective, speed density is a lot more complex and complicated to some degree to tune in, especially if you're working with a brand new setup and you don't have some existing VE maps to start with. But from a getting around the MAF sensor limitations, speed density does solve that. And it does so by calculating the airflow that way.
So there's a couple other of advantages to speed density too, especially when you're talking about rotated turbos and even from a some of the simpler stuff. But a rotated turbo, because what you have done is basically move all your sensors either near your throttle body or they're actually on your intake manifold itself. Anything that happens before that is pretty wide open. This is why with a speed density setup, atmospheric blow off valves are now okay. That is something that, gets brought up a lot. Can I just run a blow off valve versus a recirculation valve? If you're on a mass airflow sensor car, you really should be running a recirculation valve. But if you go speed density, it doesn't matter. You can let that air off and it doesn't think the air is there because it is let off before the ECU thinks it's there. The other nice thing is it makes it much simpler to make intakes and stuff like that. So big rotated turbos, they're not using stock air boxes. They're using much more basic 4-inch monstrosity intakes with giant filters and shit.
Well, and you're ignoring the bros that run their fat PTE with nothing on it, just sucking that dirty air and rocks and whatever else.
You
don't even need an intake, do you?
You don't even technically need an intake. Because it's reading at the manifold. So
yeah, man, just stick that turbo in your fog light hole and just let it eat that gravel. Who cares?
Bud.
maybe put a turbo guard on it, like a little screen door to keep the big rocks out.
And you can catch it on video when it gets sucked in and destroys your $3,000 turbo.
It's fine. Anyway, but yes, you're right. It really opens up to do whatever you want because you're right. In most cases, there's no sensors that are pre-turbo. Now, on our cars, for example, we are putting a TMAP sensor pre-turbo because we're interested to know the temperature of the air and the pressure of the air.
You can't throw a new term out there without giving an explanation.
Oops, my bad.
What is TMAP?
Are you asking me now?
Yes. Explain TMAP right now.
So TMAP is a very unique sensor. Well, fairly unique sensor. It does actually exist on the FA cars. The FA cars do use a TMAP sensor. So their map sensor also is a combined temperature. So the TMAP sensor is a temperature and map sensor in one unit. So it's a single sensor that measures both the pressure of the air and the temperature of the air.
Yeah.
So FA24 and FA20, their map sensor has that. So they are measuring the temperature of the air going in the engine. And they also have a separate, intake air temperature from the MAF sensor as well. So they have two readings. If you talk about adding a TMAP sensor onto an EJ engine, then you're moving into the conversation of standalone ECU. Yes. And generally you're moving into the conversation of using something like Mtron, like we do on our cars. And we're putting that TMAP sensor, maybe one, maybe two, but primarily we're putting one in front of the throttle body so we can measure the pressure before the throttle body and the temperature as well at that location, because we need temperature before the throttle body anyway for speed density. So that's something we kind of glazed over when we converted a Subaru, even with Cobb, to speed density. We do have to break out the temperature sensor and put it after the turbo, after the intercooler, and before the throttle body, because the temperature of the air heading into the throttle body is important.
The throttle body as you can, because what you're trying to do is calculate the air post intercooler and the closest that temperature is going to be before it goes into your intake manifold. So it has the ability to calculate the most accurate temperature it can. If you're pulling temperature before your turbo, that's not taking into the fact that you have when you compress air, it gets warmer, and that's why we run an intercooler. And then the intercooler then cools it back down. You have to know all of these things. If it's a really hot day, it's got to make compensations for that. If it's cold, it's got to make compensations for that.
But back to the TMAP sensor. So if let's say you're putting an Mtron on your Subaru and you're going to take advantage of the throttle mass flow for part throttle fueling, you're going to put a TMAP sensor before your throttle body, and that's going to give you essentially your pressure before the throttle body to use and compare it against your pressure in the intake manifold. Now, these two pressures are going to match pretty closely when you're full throttle, but they're going to be different when you're not. So that can be used for different tuning strategies. That can be used for boost management. So you manage your boost pressure when your throttle isn't all the way open. That can be more ideal. a lot of vehicles like Ford EcoBoost, even the GR Corolla, they have T-map sensors. Some of them have multiple T-map sensors to measure pressures and temperatures at various points for more accurate calculations and more accurate boost control.
If you guys want to wonder why some of these European cars, especially when they're brand new, drive so damn nice, a lot of it is due to this sort of shit. And
It's
you can
all
get
these
some of
sensors,
this sort of
and
shit
it's
with a
yep.
standalone.
And I remember I said that an ECU is a fancy airflow calculator, and the more fancy you get with it, the more smooth the engine runs. You're able to calculate the airflow at different throttle positions, throttle changes, so much
Yep.
more accurate. The fueling will be more accurate, the torque will be smoother, and you'll have a better driving car.
Okay, I got a good one here for you, and then we're going to get into some fun stuff, and then I will kick you the hell off of here, okay?
All right.
What is load?
Load. All right. So load is basically it's an ECU's way of kind of creating a single point in which to map things against. Sometimes it is a ratio of manifold pressure to atmospheric pressure. Sometimes it's taking into account the calculated airflow and scaling that to some number. Okay. And sometimes it's a number, sometimes it's a percentage. This is where different ECUs can vary a lot. Subaru calculates it out to something that, from my understanding, roughly equates to where a load of 1 is basically atmospheric pressure and a load of 2 is roughly 14.5 psi of boost. Again, not necessarily exactly like that. I know some people might jump on me, but it kind of works out like that. So in Subarus, if you're looking at the data and you're looking at the load, they idle with a load of somewhere around, let's say, 0.15 to 0.2. They cruise with a load somewhere around 0.5 to 0.9. And if we're talking about, let's say, an EJ engine going full throttle on a stock turbocharger, they'll peak at a load somewhere around 3.5, and they'll taper down to a load somewhere around, let's say, 2.8. What does any of that mean? Not really much to you, but essentially that load number goes to your ignition mapping, it goes over to your fuel mapping, and it allows you to tell the ECU what you want for fuel targets and what you want for ignition advance at those different load points. That's kind of how it works in a Subaru. Because they're sort of loosely torque based on the pedal side and the pedal demand, and then they're mostly just load based for these targets. So that's what load is.
There you go.
It goes up with air in your engine. The more engine, the more air you're putting in your engine, the higher your load. That's basically what it translates to.
So then you just said something about torque based. Or torque request, or what are you saying how are you requesting torque, and what does that mean from the tuning side?
So requesting torque, again, Subaru uses it pretty loosely. They've got it's the pedal. Basically, they're modern ECUs. They're drive by wire, which means when you put your foot down, you are essentially asking for throttle opening, but more specifically, what they can do is they can map your pedal input to a torque demand.
Yes.
And we're talking about like basically controlling the amount of torque coming, that the engine's producing. And obviously a big component of that is throttle opening. If you have the throttle open more, you're going to have more airflow that can be allowed in, you're going to have more torque, but it can also control things like your boost targets and your it can be used for limits. So Subaru essentially uses the torque request to look up boost targets, but then it doesn't actually care about producing that torque, if that makes sense. Whereas in some other ECUs, like the GR Corolla, let's say, for example, that ECU actually does use the torque to drive the boost request, and it will vary with that torque request. So it can be, German cars are completely torque based to where you don't even have a boost target table on some of these cars. You have a torque table. If you want more boost, you tell it, I want more torque.
Yes.
So that's what torque based means. Subarus use it kind of loosely, mainly for boost target and pedal response, pedal mapping.
So a term that gets thrown around a lot is lugging an engine. Okay. And I try to have this conversation with people who are, I'm trying to explain to them, more than likely how they blew their ringland or shit their bearing by ripping down the highway. They're like, all I do is, I'm pretty easy driving in 6th gear all the time, so I don't understand how this happened. I kept it at a low RPM, and this is probably their first turbocharged vehicle, and they don't quite understand that. Can you kind of explain what that looks like from a on a tuning side? What happens if you're requesting a bunch of torque, or asking for a shitload down low, and what's happening and why that can be really rough?
Yeah, so lugging an engine is basically, if we're talking about like a manual transmission car, lugging an engine is asking for too much. I'm trying to think how to break this down. Very simple.
It's tough.
Essentially, it's giving it too much throttle in too high of a gear. So let's say you're cruising along at 60 miles an hour in 6th gear, and you don't want to just pick up a little bit of speed to pass the car. You want to like give it all the beans. If you step on it in 6th gear at those RPMs, that's lugging it. It will build the boost pressure, and it will make the torque, but it's going to spend a lot of time at those higher cylinder pressures versus shifting down to a lower gear and letting it sweep through the RPMs. You're essentially going to be sort of like, it's the ultimate way of lugging an engine would be like brake boosting. Okay.
Yes.
You're holding the brake and you're holding the gas at the same time, and you're forcing it to make torque, but you're not allowing the engine to sweep through the RPMs. Lugging it is essentially doing that. You're in a low gear, you're flooring it, and you're just making it go.
And you're
to try to rev out rather than grabbing 4th gear and letting it wind out in more efficient areas and less stressful areas of the engine. Does that make sense?
The easiest way I've found to explain it is your engine is efficient within a certain range, and you're not helping it when you're trying to ask it to perform outside of its efficiency. If you want your engine to perform, let it perform where it's efficient. In most Subaru engines with the turbochargers they run and stuff, 4,000 or 5,000 RPM is where it's going to be pretty damn efficient. Okay, no matter really which turbocharger you're running. So if you're on the interstate and you're going to make a pass on a semi or whatever, and you're rolling around at under 2,000 RPM and you just smash the gas, you're asking this engine to perform well outside of where it's efficient, and what you're doing is creating a bunch of heat, a bunch of boost for almost no acceleration, where it would have been so much easier on the engine if you use this magical thing we call a manual transmission, and you just go down a gear, put this engine in its efficiency range, which is probably 1,000 to 1,500 RPM higher than where you were at that point, and the engine will accelerate easily with no issues, and it is so much easier on that engine. If your foot's to the floor, even though the RPM isn't high, you're still creating all that heat and energy. You're just not going anywhere.
Yep, essentially, yeah, and it's a lot easier to build up. Like if let's say you're knock limited, it's a lot easier to see some knock in 6th gear, low RPMs at full load than grabbing 4th gear. That the engine tends to be more sensitive in those areas to detonation. So why would you want to spend a bunch of time in that area at high loads? You don't.
Yep. All right. Now we can start getting into some of the fun stuff. What is launch control?
Launch control. Okay. So before people pop in and say, "Oh, give me that 2-step."
Yep.
Two-step.
I want
Anyway,
two-step.
launch control is a method of being able to have a controlled point to which you can take off from a standing start.
Yep.
Okay. So rather than, if you don't have launch control and you want to launch a car, you'd have to just, you could hold it on the rev limiter and dump the clutch, or you could try to rev it up and kind of hold it with your foot around 5,000 RPM and then let the clutch out and hammer down. What launch control does is it gives you an RPM point in which you can just go full throttle and it will hold the RPMs at that point. In its simplest form, that's launch control.
Yep.
So let's talk about Cobb. Cobb launch control, all it's doing is it's taking the normal rev limiter and it's changing it to whatever you set on your access port, say 5,000 RPM, and it just simply does a fuel cut at 5,000 RPM, the same as it would if you were at the 7,000 RPM rev limit, let's say. But it allows you just to be able to hold your foot down, hold 5,000 RPMs without having to try to figure it out with your foot, let the clutch out, away you go. Launch control on an aftermarket ECU is much more involved. In those cases, generally what you're trying to do is also spin up the turbocharger, if it's a turbocharged vehicle, and have some boost pressure and have some available torque to deliver as you let the clutch out and take off, assuming you have the traction for it, you have some decent tires and whatnot.
Sure.
And that's going to be using a more precise, more controlled cut of the engine. It could be fuel cut, could be spark cut. It's going to control the ignition timing, and you generally, retard the ignition timing to, again, build your boost pressure up so that you can launch your car with some torque, with some boost. So that's launch control.
What is two-step?
Maybe Tim, where's two-step Tim? Can Tim tell us what two-step is? I think two-step, the term comes from, obviously it's a country music dance, but besides that, I think where that came from is basically it's a two steps of launch control. I don't even know what I hate that term so much because it just sounds so dumb.
My understanding of two-step, if anybody's pissed off, is basically it's launch control that is using, we're going to go into anti-lag here in a second, but essentially it's using different strategies of throwing fuel and retarding timing to try to build boost, and then from that you tend to get like backfires, and that step would be, it's a second step in your RPM sweep. So that would be your one step as I hold it here, that's launch control, and then that is how I've always understood it. That is two-step. But that's why you have people, I want a really aggressive two-step so I can show off in a parking lot. What are those people doing? So if they're getting these pops, bangs, machine gun fire bullshit, like what is the parking lot two-step, and what are they doing to their engine?
Okay, so first of all, I've Googled this around every time it comes up. I think two-step is just kind of a silly term, and I wish I could understand like who came up with this. I think it's, best I can tell, it's basically two steps of RPMs. The first step is the RPM limit where it cuts the fuel and it creates the boost. And the second step is when you let off the clutch and it moves to your regular rev limit. I think those are the two steps. It's two steps of launching. I don't know. At best I can tell. I hate the term. It's so annoying. Moving on. When you're talking about hearing the pops and the fire and all that.
I want to know the two-step. When people are talking about, I want that badass two-step, this is what they're talking about.
What they're talking, because the way that early two-step systems, what they did was they basically just, as I understand it, they just interrupted the spark. Okay.
Yes.
So they're cutting the spark every so often. And that means fuel goes into the cylinder, doesn't get lit, heads into the exhaust, and then it meets the other burned exhaust where it lights, and you get those pops and those bangs and the fire in your turbocharger. So basically it's just like you're unplugging your spark plug really fast on those old two-step systems that, like the BR limiter and all that dumb bullshit we used to see people blow their engines up with.
Yes.
Those two-step systems are just interrupting the spark. And so it sounds pretty nasty. It does make some boost. Now we can do all that. We can do an ignition cut based launch control system with Mtron, for example. The benefit is, yeah, you can, if you have a really big turbocharger, it might be easier to keep it spooled up on a small engine by cutting the spark because you're using those explosions to build pressure and to build boost. Generally, if we're tuning a normal size turbocharger, a fuel cut based launch control is how I do it. It's a lot easier on things. You can still make plenty of boost pressure by simply doing the burn late using ignition timing, and then you cut your fuel to control your RPM, and that works just fine. But if you want to cut the spark instead, or cut some fuel, cut some spark, you're going to get those pops and those bangs and the fire. That's what you're hearing essentially.
What is anti-lag?
Anti-lag is a way to keep the turbocharger spooled up when you come off of the accelerator pedal. So anti-lag is most commonly associated with rally racing because in rally racing you're on and off the throttle a lot, and if you're having to do that, you're waiting for the turbocharger to spool back up. That costs you time on the rally stage. So what anti-lag does is it's a method. There's lots of different ways to do it, but it's a method of keeping the turbocharger spooled up when you've lifted off the throttle. Essentially, you don't want engine torque anymore because you need to lift for a corner, but you still want the turbocharger to keep spinning so that when you put your foot back down and need the torque again, it can produce it quicker. So that's anti-lag. And how do we do anti-lag? Well, on modern drive-by-wire vehicles, it's pretty easy. Essentially, your accelerator pedal and your throttle are not connected. So when you enable anti-lag, you give it certain parameters above a certain RPM, certain arming conditions, and essentially, when you've let off the accelerator pedal, what the system will do is keep the throttle plate open, but start to cut fuel or generally cut ignition for this purpose. It'll cut ignition events. It will retard ignition timing, and it will keep the turbocharger spooled up while producing zero or even negative engine torque. And when you come back on the accelerator pedal, it snaps back in. It puts ignition timing back in. It stops cutting the power. And boom, you go right back into boost a lot quicker because the turbocharger is spinning at higher RPM than it would be if you didn't use the system.
There are different forms of anti-lag. There are that is ECU-based anti-lag. Now,
that is ECU. So let's talk about like the rally rocket.
Just glaze on these real quick because there's a few.
We'll generalize it as an air injection system.
Yeah.
So another way to do it is to route the boost from the turbocharger. So basically, you'd kind of kick it off, but you'd bypass some air from the turbocharger spinning right back into the exhaust manifold after the engine, and combine that with fuel cuts to provide the needed fuel. And you've got air and fuel that are combusting right in front of the turbocharger that can keep it spun up that way too.
Now, all of these are extraordinarily hard on turbochargers. Okay, I cannot stress this enough. If you're listening to this and you were here for all the other Cobb stuff and just trying to get the basics, you're not ready for anti-lag, okay? Like, you're not prepared to be throwing a turbo in every other week.
You got to be sponsored by a lot more than Import Image Racing for this.
They need to be handing you turbochargers, okay?
You need a turbo sponsor.
Yes.
You better be drifting this car and making a lot of money.
If you can afford a rebuild after every event, then we can talk about it. Okay, you need to understand what you're getting into. So we just talked about anti-lag. Another thing that's getting thrown around a lot, you're hearing the bros talk about it all the time, rolling anti-lag. What is that?
Okay. Oh, okay. So this is a good one. So this is actually something that is, more purposeful and more useful, and something that we pretty much include for anybody that wants to use it on an Mtron tune, for example, or Link ECU or any standalone. It's a unique thing that standalones can do. I'm not aware of any OEM ECUs that have this functionality. It might exist maybe on some high-end stuff, but essentially what you're doing is if you're doing a roll race, so you're not moving, so launch control is used for when you're not moving. Rolling launch, or really what this is I'd call it rolling launch.
Yes.
To some degree, it is an anti-lag too, because it is keeping the turbocharger spooled up. but it's also allowing you to launch from an existing speed, a set speed, launch into acceleration without having to wait as much for the torque. So essentially what it is, you're going down the road side by side, or maybe not side by side, but let's just for argument's sake, let's say you're at a roll racing event and you're rolling side by side with another car at an airport closed off drag strip, and you're both going 60 miles an hour. That's the set fixed speed. What rolling anti-lag allows you to do is hold a button. Sometimes I triggered off the brake pedal too, like just the brake switch. So it's almost like brake boosting on crack. But you trigger the system, and at the same time you go full throttle. And what the ECU is going to do is it's going to use fuel cut, ignition cut, or some combination to hold that speed. So basically, if it's trying to make enough torque to go past 60 miles an hour, it's going to cut more, and it's going to kind of move that cut around to keep you at 60. And also doing so at the same time, those cuts and retarding the ignition timing in a fixed manner with a boost target, it's going to spin the turbocharger up and be building boost. So suddenly you went from rolling at 60 miles an hour, part throttle, no boost, to 60 miles an hour, 15 psi of boost, but essentially maintaining 60. As soon as you let go of that button, it's going to stop doing the cutting and the retarding, but you're going to be at 15 psi, and it's going to immediately transition into higher boost pressure, and you're going to have torque, and you're going to take off quickly. So basically, it allows you to launch the car into power from a rolling start.
Rolling anti-lag is freaking fun. I'm not gonna lie.
It's very fun. It's very fun.
It's good times. So
actually, Ecutech added it for the GR Corolla. I can do it on the Corolla. It can be patched in. It can be patched in on a stock ECU.
That's pretty
actually.
Sick. What is a burble tune and or
pumps
and bang tune? Whatever the frickin'
I heard Kim upstairs going, oh. All right, pops and bangs, burble, blurple. I like when people call it a blurple tune.
The blurple tune.
BLURPLE, blurple. I don't know where that one came from,
blurple.
But anyway, what it is something that, I guess it would be, maybe somebody can do some searching. I'd love to know, what is the very first OEM vehicle that did a purposeful burble tune? It was probably a BMW, maybe an Audi.
I remember the first time I ever heard it.
But essentially,
it was an 05 Mini Cooper S.
Okay, there you go.
When you got off the gas, you got pops and bangs, and it actually drove the price of those way higher than the 04 and earlier because of the pops and bangs.
So what a burble tune aims to do, and let's just talk about it like in an OEM form, because OEM vehicles come with burble tunes.
Yep.
What a burble tune aims to do is to capture the sporty exhaust crackle that you can hear on old race cars, rally cars. When they lift off the throttle, you'll hear crackles and pops, because a lot of times when those cars are racing, the fueling doesn't get turned off when you lift off the throttle. On pretty much any modern, OEM vehicle, when you lift off the pedal, within a pretty short window of time, the injection and the fueling turns off and you're coasting. This is done to save fuel primarily more than anything.
Mm-hmm.
So you're coasting down a hill. It's not sitting there supplying fuel to the engine. And that also provides more engine deceleration and yada, yada, yada. But essentially the fuel turns off. But a lot of times on these old cars or these race cars, the fuel didn't turn off. So there'd be some overrun fueling, and this would get into the exhaust and make pops and crackles and bangs. And basically the OEM manufacturers said, hey, we can tune this in. This isn't hard to do. Leave the fueling on a little bit longer when they lift off the pedal, retard the ignition timing, and you can hear those crackles on your Mini Cooper, and we can sell more of them.
Yep.
Because people want their Mini Cooper to sound like the car they heard on the internet.
Yes.
That's what a burble tune is essentially the OEMs making these cars sound sporty like you hear on sports cars on TV. And then obviously, people with a Subaru has never created the burble tune. Subaru doesn't make any of their vehicles burble on purpose. But of course, people with Subarus, they're jealous of their friends with the Ford Focus and the Audi and the BMW that have pops and bangs and crackles, and they want that too. So it became a thing where tuners started poking around in some of the available tables to see if we could get a Subaru to make the same effect. We can't do it with a direct burble system control like we can like a Ford Focus, like tuning a Ford Focus, for example. You can check a box, turn on burbles, and you have 10 tables that are related to the noise. My Audi RS3, I kid you not, my Audi RS3,
so
it had 30 to 40 tables called burble sound tuning. You could decide what gear, how long, how loud.
That's so
it was
ridiculous.
A whole thing. So these OEM vehicles with factory burble tunes dedicate mapping and logic to this whole thing. It's insane. But in a Subaru, essentially what we're doing is we're manipulating some existing tables to create the same effect. When the person lifts off the throttle, or if they're just really light on the throttle where the fueling is still on, but the engine's starting to transition into coasting areas, and we do the right thing with the ignition timing, we can create some pops. If they put a louder exhaust on the car, they'll hear louder pops. We can, to some degree, play with the sound of it, but we can't necessarily make it shoot flames and sound just like this rally Subaru you heard on the internet. But we can sort of create the same effect. And so that's a burble tune.
There you go. And I got to be real, they're the most obnoxious sounding thing on 350Zs and anything with that oh my god, they're so bad. Sometimes they sound like straight up gunshots. It's just
awful. And that's the thing is, if you take a stock BMW and you gut the exhaust, it'll make the gunshot noise with the factory burble tune.
So
burbles can be programmed to be louder or quieter to some degree, but more of it comes down to whatever the person is choosing to use for an exhaust and how that's going to sound. I can use the exact same burble mapping on two different cars, and one guy's car might sound like shotgun going down the road. The other guy's sounds like a BMW, and arguably it might be kind of tasteful to the right set of ears.
Sure.
So some of it depends on what the person puts on their car. It isn't always, oh, that tuner makes super loud burbles. No, it can be how the customer sets their car up.
Okay, I got two more, and then maybe we'll take a question because there's a decent one in the audience. We'll chat with him a little bit.
I might have to kind of pay attention here to my C8 tune while we're doing this, but I'll multitask.
We got just two more. These are fairly simple. What is rotational idle?
Rotational idle. Okay, so what that is that's kind of the other component to anti-lag. And the purpose of rotational idle is to accelerate cylinder cooling when anti-lag has been used. So again, going back to a Subaru rally car as an example, they run an anti-lag system while they're racing to have instantaneous boost response. But then when they come down to the end of a stage, they'll switch over to rotational idle. And basically what it boils down to is it's in a rotating fashion, it's not firing certain cylinders. So basically it's turning off the fuel to cylinders in a rotating pattern to help cool them down faster. Because anytime, even at idle, if you squirt fuel in a cylinder and you light it, it is putting heat in the cylinder. But if you skip doing that, if you skip putting the fuel in and you just sweep the piston through the cylinder with just air, it's going to help cool the cylinder down. But the worst thing you could do is, like, after you've been running anti-lag in a car like this, the worst thing you could do is come to a stop and turn the engine off. Some people might think, oh, I'll turn the engine off and let it just cool down. That's one of the worst things you can do because you're no longer circulating coolant and the cylinders are extremely hot from using the anti-lag. But rotational idle, by turning off the fuel to a cylinder in a rotation, you allow it to cool down the cylinders quicker, but still keep running. You can't cut too much fuel and you can't cut them all because the engine would stop, of course, but you're basically doing some cuts like that to cool the cylinders. Now, it also makes the car sound like it's lopey and cammed, and typically at the same time, you have to raise the RPM a little bit so it doesn't stall, but that creates that signature rotational idle sound. But that's what's happening.
There you go. Last one that I want to make sure we get, flat foot shifting.
Oh, okay. All right. Good one. Yeah. So flat foot shifting or no lift shifting, essentially what this aims to accomplish is that you can shift an H pattern car without having to lift off the throttle pedal. typically on a synchronized gearbox, if you don't lift off the throttle pedal and you try to clutch, it's not going to want to go in the next gear because there's still torque being produced. So what flat foot shifting does is it cuts the torque in some sort of a controlled manner. When you typically trigger it by pushing the clutch, it cuts the torque but maintains boost pressure because you're not letting the throttle close by keeping your foot down. And then when the shift has happened, either based on sensors that tell it or based on a timed period, it will resume the torque by removing a fuel cut, reintroduce the ignition timing, and you'll be immediately back into the torque. So basically it reduces the amount of downtime between shifts and also allows it to shift.
Now, here's what I'll tell you from personal experience. Flat foot shifting is good for time. It is very, very, very hard on your transmission because your synchro still has to do a lot of work. And it's also hard if you're trying to He-Man shit. Don't He-Man.
What I'll say to that is sometimes, to some degree, like a really well set up flat foot shift cut can actually, in my opinion, arguably be smoother than a lift shift.
I agree with that.
A lot of times it'll put the RPMs in the perfect spot for you to find the next gear. What you accurately did say there is because when people are flat foot shifting, they're also usually trying to shift very quickly.
Yes.
The quickness is what can break things.
Yep.
And wear out the synchros. The synchros in a H pattern transmission are not designed to be quick, they're designed to be smooth.
Exactly. Which is why flat foot shifting in something like a when you have dog engagement gears like a sequential or a dog box or something like that, you almost have to use flat foot shifting.
You do. Those are designed to be shifted very quickly. The quicker, the better. So. Yep.
We got that was all I don't know if you had any other terms. I think we hit just about anything, but man, we got through a lot of stuff, and I think this is going to be super informative. We do got a guy in the chat who is talking to us from Sydney, Australia, which is pretty cool. And he's asking, is Cobb Access Port equipment the only trusted engine management system? Are there open source systems that can be used? I don't know how much you want to go into this. I could kind of give my 2 cents on it, but
I mean, I'll speak on it.
Yeah.
I'll speak on it. Like, I think Cobb Access Port is still the preferred system for most professional tuners, still the most ideal system. It's a handheld device that's really easy for customers to use. Open source can be very easy to use, but there's more of a learning curve to it and more risk that's, you could potentially cause a problem using open source tools. So those are better for power users. Access ports are better for someone who's literally like, what's a tune? Like if you're watching this and everything in this podcast is new to you, a Cobb Access port's probably your best bet. It comes with support. It's very easy to use. I can support it. Tuners can support it. So that makes Cobb pretty valuable, pretty important. Cobb also does a lot of custom code. They do a lot of reverse engineering. They have a lot of tuner support for me. If I run into a problem with a newer vehicle and the way it's running, I can go to Cobb and say, hey guys, here's some data. Here's what I'm running into. And their reverse engineers can find the problem. If I have that problem with open source, again, arguably, if there's somebody who's really good on the reverse engineering side of an open source piece of software, sure, they might be able to do the same thing, maybe even faster. But if open source is just, being provided by somebody who's like, well, here's the tables, I can't tell you how they work, I'm going to have a lot more support with Cobb. I'm going to be able to tune your car better. So generally speaking, Cobb is the best solution for the masses and for most situations. Open source does have its place, but Cobb is better, in my opinion, for that reason.
I've got one we kind of have to hit, and I should have had it in our, I'm actually happy somebody from the chat brought this up. Thank you, Jeremy. Flex fuel.
Oh, okay. Sure. Flex fuel. Yeah. How do we forget flex fuel?
I have no idea. I'm
my God.
sorry. So we have to talk about flex fuel.
Flex fuel. Okay. So flex fuel is basically what flex fuel is from an OEM perspective is the ability for a engine to run gasoline, ethanol, or anywhere in between up to an amount of generally 85%. Production ethanol doesn't go past 85% because you need at least 15% gasoline to keep things lubricated and happy. And You actually want more gasoline than that for winter and cold starts and whatnot. That's a whole other thing. But ethanol blends can vary, and flex fuel vehicles needed to be set up to where grandma can go to the pump, and if she sees that, man, that E85 in there is $1.60 a gallon, 87 is $2.50 a gallon. I'm going to put that E85 in there. She can do that, and then the next day she might put 87 back in it. So a flex fuel sensor tells the engine exactly how much ethanol is in the fuel mixture, so it can adjust for it because there's very different fuel needs. Basic OEM flex fuel vehicles, they don't really try to take advantage of performance benefits of ethanol. They mainly just adjust the fueling so that it runs correctly on ethanol or gasoline, but really doesn't change the performance. When we talk about doing flex fuel in a Subaru, what we want to accomplish is being able to run E85 for performance reasons, because ethanol does provide more horsepower, higher octane effectiveness, cooler air charge, all that. But doing so and just pumping it in the engine, or excuse me, pumping it in the gas tank and not knowing what the ethanol blend is, or having to always fill up with E85, even if you're traveling and you can't find it, can make running ethanol difficult, because the pump can have 60% or 80% or 90%. In some cases, maybe like out of a barrel.
Mm-hmm.
A flex fuel sensor allows a Subaru to be tuned to run any blend of ethanol or down to pump gas all in one. That's basically done with aftermarket programming that Cobb is patched in, and a sensor that sits in the fuel line and sends that signal to the ECU. So that's flex fuel at a high level.
Yep. And again, can't stress enough, ethanol is boost juice. It's effectively 105 octane, is what people have kind of equated it to, but you really can't.
Yeah.
And so
Jeremy wanted to know about, so I don't even know if Delicious Tuning still has these older flex fuel kits available. I think all their new stuff is either CAN bus or green speed. I could be wrong, but there was a point back in the day where before flex fuel tuning and logic came out, Delicious Tuning did get kind of clever and come up with a way to sort of add flex fuel to a factory tune that didn't have flex fuel logic, essentially by manipulating the intake temp signal and leaning on the intake temp sensor compensation tables to sort of manipulate the tune. I was never a big fan of it. I think fundamentally it had too many flaws to be comfortable using it. But that was a thing that existed before Cobb, that was just trying to get ahead of Cobb essentially. But then once Cobb came out with their own flex fuel, that's the sensor is sending the actual ethanol value to the engine. There's separate tables. It's all done in a true OEM style fashion.
Man, I think we kind of nailed it. I think at some point we're going to have to call it, and you've got stuff you got to do, and we're almost an hour 50 into this, and I promised an hour. So,
yep.
I appreciate the hell out of you, and I know everybody who's listened to this is going to appreciate the hell out of you. Yeah, leave us a comment if you guys like shows like this. Kind of a
maybe for a future podcast, maybe you could farm some high level questions, and we could kind of just start with some of those, and then let people ask questions, and we can just talk.
I wanna stick you down and do a ask me anything tuner deal, know? And I want to try to get some, but I really wanted to get a lot of these basic ones, because I'm getting a lot of these questions from customers, and like I've said before, Nasiak's kind of dead. This Gen Z, and that's a topic we're doing here soon. I'm going to get a bunch of Gen Z kids on, and I'm going to ask them how they learned about Subarus and why they're even into this. That's going to be a highly entertaining one, because I want to understand the mind of Gen Z.
Yeah,
but they don't even they don't touch Nasiak, and they don't search for things like that. So there's a lot of really basic stuff that a lot of newer people are missing, and they've got to the point where if they ask it within a Facebook group or something, they just get flamed. So I think I'm going to do a lot of these basic questions You know what I mean?
Yep.
These I'm gonna do another one like suspension and just other stuff where these are just basic questions. What are these things and why? So, but yeah, I can't thank you enough for being on, dude. I know it was kind of short notice, but I think we cleared a ton of ground and I think it was great. So, yeah, if anybody first time listening to this, how would they get a hold of you, you or Kim, if they needed to chat, get a tune, do whatever?
Yeah, just go out to our website. There's an email to send if you want to like kind of do some high level
What is your
consulting.
website?
What's that? Boostedperformancetuning.com.
Okay.
Yep, email is good. We use a ticket system. Kim handles all of those, all the consulting, answering questions. We have a text number that works pretty well if you have some quick questions. And there's a lot of good information on our website just to kind of figure out what you need. People who are really new might want to email in and get some answers, and people who are kind of know what they're looking for, it's easy to find on our website, in my opinion.
Yep. No, your website's super solid and easy to use. So boostedperformancetuning.com. If you got any questions on, parts or whatever, you need to bounce some stuff off me. I'm easy to find. Dewey at IAG Performance. .com for my email, or just give us a call up at IAG Performance. And yeah, I think that's gonna about end it here. So it's been real, it's been fun. It's been real fun, and we will see you guys next time.